Okay, we'll get started, I think. Welcome to the first Singularity CE community call for 2022. We had a great year last year and looking forward to more of the same this year. As always, this call is being recorded. It'll be posted on YouTube for people who aren't able to make it or prefer to watch it in the background while they're working, things like that. And we're going to start off, as we did in the 2021 meetings, with a sort of demonstration / tutorial segment to keep this relevant, not just for people who want to track the development of Singularity CE, but also users who want to learn about things to do with Singularity CE, projects connected to it, and so on. If anyone is interested in presenting in a future session to show off maybe a workflow they use Singularity for, or a project which is kind of near to Singularity, interacts with Singularity, please let us know via the Slack, the Google group, or you can email us or ping us on Twitter or anything like that. So today's kind of demo session, before we get into the talk about development and progress on CE, is going to be a quick overview of running MPI applications with Singularity. Now, this is a topic which commonly comes up in the Slack channel and on the Google groups and around other places on the web with regard to people asking questions about how do they really run MPI applications in containers, and what does error X mean, where X could be one of many different errors related to what's on their host, in their container, or a mismatch between, and so on. So I want to spend a little bit of time today, maybe about 20 minutes, giving a quick run through of how to use MPI with containers in Singularity. And this is going to form the basis of a bit of an update for our documentation. And we may turn this into a separate sort of tutorial video in the future. On the Sylabs IO site in the doc section, we have our user guide and admin guide for Singularity. And the first thing to point out is if you go to the user guide for the latest version, down on the left on the bar here, there is a section Singularity and MPI applications. And this will walk you through most of what I'm going to talk about today. What we're calling different models of running MPI, and has some example definition files here, and you can follow this tutorial along. What I'm going to be showing from my computer today is slightly updated, and I'm going to mention a few more kind of gotchas, some catches with running MPI applications, which will eventually make their way into the docs as well. So I'm going to stop my video a second and start sharing a terminal, and we'll begin looking at the MPI examples that I have here. So I'm on a machine which has an extremely up-to-date Linux distribution running on it. So I have Fedora 35 here, and on this machine, I'm currently going to be working with, sorry, not list, module avail, MPI modules. We've got an mpitch and an open MPI. We're going to start with open MPI. And if I load this module, we'll see I'm on 4.1.1, which is almost bang up to date, but not quite. The first thing to mention here is that the situation of using MPI with containers has changed a bit over time. And I'm going to demo using 4.1.1 here, which is very up to date. But a lot of material out there on the web, tutorials from HPC centers and so on, is actually referring to running applications which are using much older MPI versions, even back to sort of OpenMPI 1.x, where things are different. We'll touch a little bit on what's different as we go through. But in general, the situation is if you can use a newer version of MPI, it's more straightforward, things are more compatible, and you can deal with more mismatch between your host system and what's in your container. So I'm starting off with an example of what's called the hybrid model for running MPI applications in the container. If you look at the docs page I showed earlier, you'll have a big explanation there of what the hybrid model is and what the bind model is. When we're running an MPI application, we have to have an application which is linked against an MPI library, and then we have to have programs and libraries which work together to spawn a process in the correct place and make sure everything can get wired up so the different processes can talk to each other to do the collective processing across different machines in a cluster. Now, a hybrid model is called hybrid because the kind of complete setup for how we're running our MPI application is a hybrid of stuff from the host and stuff that's in the container. And what we do in the hybrid model is we put the MPI library and any dependencies in our application in the container, but we launch the application using tooling from the host. In MPI, there's the concept of process managers, and a process manager is the thing which kind of sets up all the communication, make sure processes start on the correct machine, are bound to the correct CPUs, and so on. And there's a history of standards in process management, beginning with something called PMI, the process management interface, then PMI2, and then we moved to something called PMIX, and then we have successive versions of PMIX, so PMIX V2 and V3, and so on. And as these have gone kind of progressively more advanced, they provide kind of greater interoperability and less restriction on matching MPI outside the container and inside the container in order to get everything to run correctly. So let's have a look at an actual example here of getting an MPI program running using OpenMPI in the hybrid model, where we're going to use most of the MPI stack in the container, but we're going to start our application with process management on the host. I've got a C program here called MPI test.c, and it's an extremely simple toy program. All it's going to do is using MPI primitives, do some setup, and then it's going to print out to the terminal for each process what MPI rank the process is. So if we run this MPI program across 8 CPUs, we should have 8 different rank processes, and we should see the rank numbers output accordingly. Let me then open up my definition file for my container. And in the hybrid model of running MPI applications, this looks a little bit complicated. So let's go through it pretty much line by line to see what's happening. At the top, I'm starting from a Docker image of Ubuntu 18.04. Now, this is the first kind of interesting point about the hybrid model of running applications versus the binding model. In this hybrid model, I'm going to install my MPI libraries in the container under the operating system that's provided by the container. So in this case, Ubuntu 18.04. My host system here was a Fedora machine, and it is much, much newer with all its basic libraries and things than Ubuntu 18.04. So if I tried to just kind of pass in all the MPI stuff from the host, it wouldn't work because my basic libraries in the container aren't new enough to satisfy the requirements of the MPI libraries on the host. So the hybrid model, by putting the MPI stack in the container, we can kind of avoid this issue. So I can quite comfortably run a several years old distribution on something which is very up to date on the host side. I'm going to copy in my test program just into the container. And then the next block, environment, sets up some variables so that my path and my library path in the container are going to contain the directory where I'm eventually going to install OpenMPI. The post block is where I'm actually installing my MPI stack. Okay, so the first thing I do is install a bunch of distribution packages. Now we're going to get compilers, which seem obvious, but then towards the end of this line, we're seeing things like munge, libmunge, libevent, lib, hwlock. And these are dependencies of the MPI stack we're going to install. We are going to use OpenMPI 4.1.1, and OpenMPI 4.1.1 supports the process management standard, the interface PMIX, and it supports version 3. Now, OpenMPI actually includes a kind of internal version of PMIX, which will build itself if you don't provide an external one. But in this case, you'll note that we're going to actually install ourselves PMIX 3.2.2 in the container before we build OpenMPI. And the reason for that is that although PMIX is a technology which promises kind of greater independence between the batch scheduler or the MPI run command used to start processes and the MPI library used by your application, there are some caveats. I'm running on a system that uses Slurm as the batch scheduler, and Slurm uses something called munge to handle UIDs and GIDs authentication across a cluster. Now, by default, when running under Slurm, PMIX is going to want to use a munge plugin to manage things, but the version internal to OpenMPI that it will build itself automatically won't set this up. So I am having to, in this case, manually install PMIX and configure it so it includes this munge support and install it in my container. Once I've got PMIX installed, I go and download OpenMPI 4.1.1 itself, and then I'm going to compile it and install it, making sure that I point it at my PMIX in my container that I compiled before. Are there any questions up to now? Okay, once I've got my MPI library available in the container and my MPI compiler, I can go ahead and compile my test application. And then when I actually run the container, I'm going to execute the test application from a run script down here. I'm just going to call this MPI test binary. So this container takes quite a while to build, as you might guess from the definition file. But I can go ahead and start using it because I built one earlier. So I had loaded my MPI module. So if I want to run using the OpenMPI MPI run and use 8 tasks. I can just say Singularity run and my container name like this. And everything is wired up nicely here. Okay, so I have OpenMPI on the host. Its MPI run command is going to interact properly with the one inside the container, and we see that it started 8 processes, and they all talk to each other properly and reported their ranks. So everything is good there. I mentioned on my machine, I have the Slurm batch scheduler. So we can see that I have nothing running here. I'm good to go and try and run a batch job. And I can use, instead of MPI run, Slurm's own runner, srun. And I can do this directly from the command line or in a batch job. And if I call my Singularity container with srun minus n8, then I'm seeing 8 MPI processes here. Now, the critical thing to point out here is that at this point, I'm not using an OpenMPI installation on the host to kind of kick off my MPI application in the container. I'm using Slurm's srun command, and Slurm's srun command is implementing this PMIX process management interface. And that's why it's able to launch the application in the container without me needing to put MPI run in there directly. So on modern MPI stacks, which support this PMIX process management interface, we have very good compatibility for launching applications. And if you have an MPI stack, an application in a container that supports the version of PMIX that is provided by an MPI stack on the host or your batch schedulers running a tool like srun, then you can successfully run an application in this manner. Our usual kind of expectation would be that in institutions, what we would advise would be that groups or system administrators can come up with some base containers which provide PMIX and OpenMPI in a container, and then users are free to write definition files which don't contain all of this stuff, but just contain the steps to add their applications into a container at build time. Any questions before I carry on? All right. The other model of running an MPI application is rather than to put the MPI stack in the container, to instead use the one that's on the host, on a host system, and just make it available inside the container for runtime. This is called the binding method because we bind all the libraries and things we need into the container. What I have in this directory is an example of doing this with OpenMPI. My definition file in this case is very simple. I'm starting with a Fedora Docker image, and I'm adding my pre-compiled MPI application into the container. And then at runtime, I just run that application. So no MPI stack is being added into the container, but I'm starting from a distribution here, which is identical to my host system. And that's important because the libraries I'm binding into the container come from this host system, and they have certain dependencies, basic dependencies such as the C standard library and so on. And I must have compatible versions of those in my container, otherwise things won't work. If I tried this with Ubuntu 18.04, it will fail. So I'm matching it quite closely to my host system here. I have my MPI test pre-compiled program on my host this time. That's gone into the container. I've built the container, and now if I attempt to just sort of run this with Singularity before doing anything else with MPI run or whatever, it's going to tell me it can't find libraries. And that's what we expect, because I copied my application in, but I haven't provided any of the MPI libraries. The way I am going to provide the MPI libraries is by binding them into the container. And the longhand way of doing this is with Singularity's -b or -- bind option, and giving it a list of everything that the application needs to run that is present on the host but isn't yet inside the container. So I have to bind in my open MPI stack, I have to bind in PMIX, and then I have a load of extra libraries here. These are related to network fabrics and things. My version of OpenMPI on my host it's been compiled to support almost everything. It supports InfiniBand, it supports OmniPath, and it supports different transport libraries for that, like libfabric and UCX and so on. So I'm having to bind a lot of stuff in, and I had to discover these libraries. So really, setting up and providing instructions for how to do a kind of bind execution is something that's advisable to be taken on by the system administrators, or the people who are installing MPI on the cluster and installing the libraries and things for any networking fabric like InfiniBand and so on. But once I've got this set up, I can either MPI run my job, and there it's successful, or I can run my job, and we have success again. Okay, so you have to kind of work this stuff out. You have to make sure your container's basic Linux distribution closely matches the host. But then what we end up with is an extremely small container, only 51 megs, without a lot of MPI stack and stuff to carry around. The last thing I'm going to show quickly is I'm going to go into a different directory. And in this directory, I have an example not using OpenMPI, but using mpitch. So I have an mpitch installation, a different MPI framework. And let's see about using this. We could do the hybrid method, but I'm going to jump straight to the bind method because I want to show you something else about how you can make that simpler to use. Let me switch from OpenMPI being loaded to mpitch being loaded. And let's have a look at the actual module file which loaded that. Down at the bottom here, you'll see that my module file is setting an environment variable called Singularity contain libs. And this is listing all the things that need to be bound in to support running an MPI application with mpitch in the container. So instead of having that horrible long command, I don't need to specify any binds on my command line. Singularity is going to pick them up from the environment when my MPI module has been loaded. Right, let's try and MPI run this. Sorry, my tab completion isn't working as I expected. mpitch bind.sif. Okay, so There we go. That worked nicely. The binds happened properly, and I'm using the same MPI stack and the host and in the container, and everything is good. Let's try with srun and see what happens. Oh, so here something's gone a bit wrong. We have 8 processes launched, but they haven't been talking to each other. They haven't been working properly as an MPI application. Now, why is that? Well, the reason is that I showed you before with OpenMPI that I was using something called PMIX as the process manager. Now, my mpitch installation doesn't support PMIX. When I use mpitch's MPI run, it's using its own native process management, so things are okay. When I use srun, it's attempting to use PMIX, and my MPI stack just won't work with that. So instead, what I can do is I can ask Slurm to use not PMIX, but PMI2. And in that case, everything runs properly because my mpitch installation understands PMI2 as a process management interface. So that's just a little kind of walkthrough some of the basic things of how to create a container that holds an MPI application and how to run it. We've got the hybrid mode and the binding mode, and we've shown how you have to consider this process management interface in order to launch the application successfully using process management outside of the container that's talking to your application and the MPI framework in the container. If anyone has any questions, please answer them now, or you can join a conversation in our Slack channel, a Google group mailing list, and so on. And as I mentioned at the start, we're going to try and work up some of this more information into improvements in the documentation and maybe a more formal tutorial session in the future. Any questions at all before we move on? Okay, so in the second half hour, on the agenda today, we have to take a little look at the roadmap for Singularity CE going forward. I want to touch on how things are looking with compatibility between Singularity CE and the Apptana project, as we kind of talked about a bit in the last meeting. But first, I'd like to pass it over to Adam. So Adam can talk a little bit about the Scilabs Library and some of the efforts around the protocol and making that a more open standard.
Yeah, cool. Thanks, Dave. Yeah, so just to, I guess I'll start with some background. So the Scilabs Library was actually something that we constructed internally to store CIF images. For anybody that's used it, will be familiar with that. This was done in right at the start of Sylabs 2018. Actually, DT himself was the primary author of the library and the library protocol. And really the point of it was at the time, OCI registries and Docker registries didn't have support for storing anything but Docker images, and people wanted to share CIF images. There's in HPC, there's obviously a considerable value that people get from using these kind of monolithic images in the CIF format. And so, it was an obvious thing to say, well, it would be nice to have a place where, a community of images could be built around HPC and shared, and, people can discover other people's work and all of that great stuff. So what we did is we made a freely available service at cloud.scilabs.io. And obviously Singularity being a open source project, we needed a client that could go with that. So in the Sylabs GitHub space, you'll see there's an SES library client if you look for it. That's been open source from the start, and that's what Singularity and I believe today even Apptana is still using for client-side support for interacting with the library over something that we're now calling the library protocol. So what's interesting is, it's natural. The container library isn't an open source product, but we do have a pretty vibrant open source community. And what happened over time was a couple of individuals actually took our open source client library and decided to make a server implementation that it could also interact with. So two examples of that, there might be more than this, but the ones I'm aware of, S-Registry, which Vanessa from our community maintains, and then Hinkskull, I hope I'm saying that right, but we've actually had that demoed on our Singularity CE community call, which again is an open source implementation of the library's API. So that's sort of the background of where we got to. We had an open source client implementation. We had our closed source implementation. We had two open source implementations that were out there. And then in December, we had someone from the Apptana TSC reach out and say they had decided originally to remove support for it, ostensibly because they didn't see it as an open standard, despite the open source implementations out there. But one member of the TSC in particular, Dave Dykstra, was pretty active in saying, well, there are open source server implementations. Really, all that we're missing is kind of a specification and a few reviewers on that. And hopefully, the TSC would follow along with that if those were in place. So Vanessa actually, kind of spearheaded an effort really rapidly to put up a repo that had a spec in it based on what the work she had done with S-Registry. And ultimately, Dave ended up reaching out on our Google group and saying, it'd be great if you guys could contribute to this effort. And so we discussed it quickly, internally. Also, we've always been really in support of open source. Singularity CE will always be open source. And so, it looked like a no-brainer to contribute to that effort. And when we talked about how we could do that, what that would look like, we said, well, we do have an open API spec, which is kind of what we've been using internally. And we hadn't checked that in with our client library. So we had an implementation of that standard, but we hadn't actually published it. So that day, I think it was, I just checked that in, and then we kind of agreed to contribute that to the effort that Vanessa had started, and that now lives in a registry or in a repository on GitHub that has a few people signed up as maintainers, myself included. I guess overall, the view from Sylabs is we're really happy to see that both there's many implementations of that standard now that was developed at Sylabs, and also that there was a lot of community support for maintaining that support in the Apptana project going forward. I think there's a lot of value that people have published into that container library, and also the other S-Registry and Hinkskull as well. And so it looks like going forward, that project intends to maintain support for the library protocol. We're going to continue to maintain, obviously, our cloud library because it's got a lot of good content in it, and that continues to remain freely available at cloud.sylabs.io. And really, we're just looking to see, how that evolves going forward. The last thing I'll say is I think the landscape has switched slightly. In the last couple of years, OCI registries now do have support for kind of arbitrary formats through initiatives like the ORAS standard. So, even as a team, we're really keeping our eyes open. The library is not going anywhere, but we're always looking for how we can work better with, OCI registries, how we can make the library better. and ultimately make Singularity CE compatible with every workflow that anybody's ever done. So yeah, I guess that's about it from for an update on the API spec. We certainly welcome contributions and extensions to it. We'll be engaged if there's as that API continues to evolve. And I think that's about it. Dave, I'll pass it back to you.
Thanks, Ed. I think that's a great overview. And if there are no questions, I mean, we can summarize a little bit more how things stand between Singularity CE and Apptana now. So last month, it looked like all of the library remote build and the Sylabs key store kind of integration that's present in Singularity CE would not be present in Apptana. Now, through the work that Adam's just mentioned and readoption of the library protocol into Apptana, the situation going forward is that it looks like Apptana 1.0 will basically be the same functionality set as Singularity CE 3.9, which we released last year, with the exceptions that remote build support won't be present. So you won't be able to use the free remote builder at the cloud.sylabs.io from Apptana, nor would customers of Singularity Enterprise be able to use Apptana open source to interact with their enterprise installation fully. Apptana won't point by default to the Sylabs key store, so that if you are using images which have been signed with keys that have been put into the cloud Sylabs.io key store, you won't have those sort of automatically retrieved and the validation performed in that kind of streamlined manner. And then for the library functionality itself, though it's been added into Apptana again and will be present for their first release, the Scilabs library won't be a default configuration. So it will require some manual work to make that available to users for them to pull directly from the Scilabs library if that's what you want to do there. So I think that's a fair summary at this point of the differences based on what we've seen progressing in the Apptana repositories versus what was released towards the end of last year in Singularity 3.9. Any questions there? Okay, let's jump on to the last topic for this morning or today, which is the Singularity CE roadmap. So we've updated this and cleaned it up a bit following the release of 3.9. So we're now looking forward to Singularity CE 3.10. In a previous meeting, we talked about why we've decided to go for 3.10 now, rather than kind of more fundamental changes that would require a 4.0 major version. We're really concentrated on keeping things stable and moving forward and adding features in a way which doesn't cause a lot of turmoil for people. So our current release, CE 392, was on December the 10th. And if you scroll down here, you'll see that our development cycle continues to be 6 months. So 3.10, we aim to release it in May. Now, in 3.10 at the moment, we have these features kind of tentatively assigned. So can run through these quickly. We added support for C Groups v2 systems in 3.9. C Groups v2 and System D allow you to have a delegation of C groups limits, such that a rootless user can set up limits. So we want to make that possible in Singularity CE, and also properly enable the C group namespace, which is important for having a sensible view of things from inside the container. For a long time, Singularity CE has had the ability to apply SE Linux, AppArmor, seccomp policy on containers, but it only works as root because only the root user can use this -- security flag. Now, in a previous version, we started to let administrators bless certain container networking configurations so that they could be used by users. And the idea is that this should be possible as well with configurations to restrict operations using these security methods. So it should be possible for a sysadmin to actually use seccomp filters to restrict things further than the kind of POSIX, UID, GID, and file permissions model that Singularity uses as its primary means of security. So we're going to look into default or sort of blessed configurations. There's a lot of code throughout CE which is there because we supported Rails 6 for a long time, and that didn't provide much of the kind of basic kind of primitives and things that are useful for full-featured containers. So we had workarounds, and some of the programs we call out to are old in Rails 6, and we had to work around flags and things. And I mean, this is internal work that we'll be doing, but the expected benefit of removing some of this legacy code is to reduce the complexity and improve our testing of some areas. This item here, the Docker OCI compatible argument and envar handling, this is kind of a big item. Now, there's an issue which nicely kind of explains what this is all about. But in a nutshell, Singularity was originally written in C and shell script, and it was a very natural thing to do, to have definition files and run scripts and environments set up be shell scripts, which are evaluated. And the way in which Singularity evaluates these run scripts and things affect how arguments that are passed to into a container when you Singularity run it, and environment variables through the various means you can kind of pass them in are dealt with. Really what happens is that Singularity can evaluate or kind of consume one level of escaping often in these arguments and environments. Whereas with OCI Docker containers, you don't get that. So Singularity doesn't behave exactly the same as Docker or OCI when you have arguments or envars, which include sort of escaped dollar variables or certain nested quoting and so on. And this is a little bit of a problem for compatibility, but it's not something that we can trivially change, because the current behavior of Singularity is exploited by many people out there to do specific things. Lots of people really like to blur the lines between the host system and the container in their definition files, and evaluation of envars or args and things it's actually used out in the wild to do this. So in 3.10, what we want to do is introduce a mode in which Singularity behaves the same way as Docker and OCI, but it's something you have to turn on. and we make that available for compatibility, but we don't have it by default. We look at possibly it becoming the default over time. The bottom two are kind of follow up from the 3.9 work to use NVIDIA's own NVIDIA container CLI to set up GPUs in the container. The way in which Singularity sets up its fake root environment isn't currently compatible with using that. So you can't use that functionality with fake root right now. And we would like to move probably toward the NVIDIA supported method being the default way of performing GPU setup, with the binding method that Singularity has always had as a fallback rather than the default. So these are the things we've kind of got tentatively under 3.10 at the moment. We have some future features listed, things which could happen in a 3.x release. We have some features which are really affecting the CLI or a major kind of rework of code, which probably fit more in a 4.0 at some point in the future, perhaps. And then we have our nice to have list down here. So what we're really looking for at this point is if people in the community are interested in these features, are they actually useful? There are certain things here we definitely want to pursue ourselves in Sylabs for reasons of compatibility with modernizing Linux distributions and so on. But we'd hope that some of these are also useful for people out in the field, as it were, at HPC centers and so on, particularly this OCI Docker compatibility. So we're really looking for feedback on this. Any suggestions for kind of extra stuff which you really kind of desperately want in 3.10, and you can directly comment on the roadmap. There's a HackMD button at the top. This takes you through and you can log in with a GitHub account, and then you can comment on and edit the roadmap in HackMD directly, or you could file issues in the GitHub repository, or you can talk to us on Slack. If there are any things that aren't covered in the roadmap, and there may be smaller changes that you think makes sense in Singularity and you might want to tackle yourself and have a go at, please reach out to us and let us know. And we'd love to kind of help you get started, give you pointers of the right direction of which bits of code to look at, talk about how to make changes fit in consistently with the CLI and so on. We're really hoping that we can get additional outside contribution for some of this stuff this year, and we're very keen to help people do that and help people bring their code into the project. As we said before, we're very committed to open source, and everything remains under the same license as it's always been, under a BSD license, and we really want to help get people involved so that maybe if you have something which is a particular need urgently for you, then that can happen faster than it otherwise would. Okay, any questions on the roadmap? Okay, so I guess we've gone through the content which we wanted to talk about today. It's been a lot of me talking. I had to talk quite a bit, quite a lot of material. Do we have any other topics? Anything someone wants to bring up before we call it for today? All right then, we'll end slightly early, and this video will go up. If you want to follow up on anything we've been talking about, Slack is probably the best place, but the Google Roots mailing list and so on are available there too. Thanks for coming, and thanks for watching this. If you're on YouTube, hopefully it's been a useful few minutes of your time.
Thanks.